In this session, we turn our head towards one more beautiful topic in matrices, that is rank of a matrix. After noting down the usages of inverse of a matrix, there has been one more usage of inverse of a matrix, that is solution of linear equations. And in order to get entered into that topic, we must be aware of rank of a matrix. Yes, these are all linked together. Again, to know the rank of a matrix, there has been one more topic, namely minors in a matrix. You may ask me a doubt. Sir, already we have discussed with the minors of elements of a square matrix, Of course, these minors, in order to have these minors, we need not be provided with a square matrix. In any matrix, of course, we will be able to form minors. What are minors? Yes, minors in a matrix. We are now interested to learn. After understanding them carefully, then we shall switch over to the topic rank of the matrix. Therefore, it is necessary for us to know about minors in a matrix thoroughly. Let us do it. Observe the matrix. 1, 2, minus 1, 3, 4, 5, minus 2, 6, 0, 4, 3, 8. Is it a square matrix? No, it is not. It is a 3 by 4 matrix. Well, to have the determinant of a matrix, you must be provided a square matrix. Okay, come on. Suppose I delete the first column from this matrix. What happens? 2, minus 1, 3, 5, minus 2, 6, 4, 3, 8. That will be a part of this matrix, isn't it? That part which is obtained by deleting a row or a column, some rows or some columns from a given matrix is called submatrix of the given matrix. This is one submatrix. You omit this. Another 3 by 3 submatrix is there. 1, minus 1, 3, 4, minus 2, 6, 0, 3, 8. If you omit this, one more 3 by 3 submatrix will be obtained. If you omit the fourth column, one more 3 by 3 submatrix will be obtained. Okay, friend, can you have a 2 by 2 submatrix? Why not? You delete the first row, first column and second column. This will be the 2 by 2 submatrix. Well, we could have understood about the submatrix of a matrix. What is a submatrix? That is the matrix obtained by deleting some number of rows, some number of columns, or both is a submatrix. Well, out of these submatrices, let us concentrate on square submatrices. Let me delete the third column. The square submatrix is 1, 2, minus 1, 4, 5, minus 2, 0, 4, 3. As it is a square submatrix, it is possible to have its determinant. How many such determinants are possible? If you omit fourth column, this determinant is obtained. If you delete third column, one more 3 by 3 determinant will be obtained. If you delete second column, one more 3 by 3 determinant will be obtained. Like that, how many 3 by 3 determinants can be obtained from this? 4. These are called 3 by 3 minors of A. Give me an example of another 3 by 3 minor in A. What is that? Let me delete the third column. 1, 4, 0, 2, 5, 4, 3, 6, 8. Another 3 by 3 minor. I want to have one more 3 by 3 minor. Can you? Why not? You delete now the second column. What happens? Another 3 by 3 minor is 1, 4, 0, minus 1, minus 2, 3, 3, 6, 8. In a similar fashion, if you can delete the first column, one more 3 by 3 minor will be obtained. 2, 5, 4. minus 1, minus 2, 3. 3, 6, 8. Well, my dear, what are all these? Determinants of square submatrices of 3 by 3 order from A. Those are nothing but called minors. This is a 3 by 3 minor. I want to have a 2 by 2 minor. Can you? Why not? This is the 2 by 2 minor. Another 2 by 2 minor. Of course, this is another 2 by 2 minor. This is another 2 by 2 minor. 2 minus 1, 5 minus 2. Like that. So, by observing all these, what can we understand by the word minors in a matrix? Whatever might be the nature of the given matrix, whether it is rectangular or square, it is just immaterial. We will be able to have the minors. How? How can we define? Minors in a matrix are the determinants of the square submatrices formed from A by deleting some rows or some columns or both. These are minors. These are minors. Good. Next, it is enough for us to have the meaning of minors. Let me give you one more example of a matrix. 1, 2, 3, 4, 2, 4, 6, 8, 3, 6, 9, 12. What will be the shape of this matrix then? This is a 3 by 4 matrix. 3 rows and 4 columns. Can you give me a 3 by 3 minor? 2, 3, 4, 4, 6, 8, 6, 9, 12. Its determinant. What is its determinant? 0. The elements are proportional on the rows. This is 0. This is 0. This is 0. So, you are not able to have a non-zero minor of order 3. Well, I'm changing this to be some 16. Now you tell me, can you have a non-zero minor of order 3? You cannot. Can you have a non-zero minor of order 2? As of course, this is the 2 by 2 minor. 32 minus 12 is a non-zero minor. Okay, what is the benefit for us in discussing that problem about minors? That is of special interest is the case to deal with the rank of a matrix. Yes. Now, let us get ready to write the meaning of rank of the word, the absolute meaning. Let us try to understand. Let capital A be an m by n non-zero matrix. Non-zero matrix. So, the very first sentence itself tells us that rank of a matrix is defined for non-zero matrices only. Of course, some authors used to define the rank of a zero matrix as 0. We're not interested in it because it is neither harmful nor useful. That is why let us not bother about it. But in the beginning, we define the rank of a matrix A only when it is a non-zero matrix. Well, the rank of A is denoted by row of A, denoted by, see, even though it is row of A, we read it as rank of A, as follows. Rank of A is equal to small r if and only if, number 1, there is at least one r by r minor which is non-zero. What do you mean by R minor? That submatrix of A containing R rows and R columns with determinant not 0. Number 2, the second condition. Every minor of order R plus 1 or more is 0. Then only we say that the rank of the matrix is R. My dear friend, you please notice the two sentences firmly in your mind. I shall try to make them clear by means of an example. First rule is rank of A is equal to R if and only if there is at least one R by R minor which is non-zero. That is R by R determinant of the submatrix which has been obtained from the main matrix. Of course, that can be obtained by either deleting a row or a column or both. Yes. And every minor of order R plus 1 or more is 0. That is the rank of a matrix. Now let us try to understand this definition carefully by observing some examples. Well, we have taken the definition of rank of a matrix. There are two conditions. By clubbing those two conditions, we can frame one useful sentence. What is that sentence? The largest possible order of a non-zero minor is nothing but the rank. Yes. You can understand what is the reason for me to say this sentence. Yes, you observe the example. Let A is equal to 1, 1, 1, 1, 1, 2, 1, 4, 5, 2, 1, 1, 1, 1, 1, 2, 2, 2, 2, 2. What is the type of this matrix? 4 by 5. What is your purpose? We want to find the rank of the matrix. Well, we have noted the definition. In that, there are two conditions. Of course, by clubbing those two conditions, we could have designed one sentence. The largest possible order of a non-zero minor. Well, to approach the rank, you first notice the largest possible order of a minor here. It is 4 by 5. Can you have a 5 by 5 determinant? No, not possible. 5 rows are not available. Can you have a 4 by 4 minor? Yes. What is the largest possible order? 4th order. You check all 4 by 4 minors. Come on. Suppose you delete the first column. 4 columns will be there, 4 rows will be there. What is its determinant? 0. Why? First row and third row are same. This is one of the 4 by 4 ordered minors. It is 0. Another. Again 0. You observe? First row, third row same. Next one, this is. Omit this. Again 0. Omit this. What is the 4 by 4 minor? 1, 1, 1, 1. 2, 1, 4, 2. 1, 1, 1, 1. 2, 2, 2, 2. 0. Again the last minor. Remove the 4th column. 1, 1, 1, 1. 2, 1, 4, 5. 1, 1, 1, 1. 2, 2, 2, 2. Again it is 0. So, it is an easy matter, of course, to observe that every minor of order 4, that is 4 by 4 minor, is 0. Very sorry. So, rank cannot be 4. Why? If at all rank is 4, you must be able to find at least one 4 by 4 non-zero minor. Not possible. Well, come down. 3 rows, 3 columns. To have that, you must omit 1 row and 2 columns. Okay. Delete the 4th row and delete the last 2 columns. 1, 1, 1, 1, 1, 1. Sorry, 0. Last 2 over this and this. Remove. Again 1, 1, 1, 1, 1, 1. 0. Again, you observe any 3 by 3 minor. All the 3 by 3 minors are zeros. All the 3 by 3 minors are zeros. So, rank is not 3 also. You take any 3 by 3 minor, whatever 3 by 3 minor you take, you omit the first row, 2, 1, 4, 1, 1, 1, 2, 2, 2. What is the benefit here? If you drag 2 out, the gain is 0. Therefore, particularly for this matrix, it is not at all possible to have at least one non-zero minor of order 3. There is no 3 by 3 non-zero minor. Every 3 by 3 minor is 0. Therefore, we cannot say that the rank is 3. Firstly, we have tested for 4. There is no 4 by 4 non-zero minor. Leave it. Next, we have tested for 3. There is no non-zero minor of order 3. Leave it. Come to 2. 2 by 2. Is there any 2 by 2 non-zero minor? Oh, there are plenty. This is 2 ones are 2, 2 minus 1, 1. Happy. Therefore, rank of A is equal to 2. Come on, friend. 2 is the largest possible order of a non-zero minor. If you want to have a non-zero minor, you can have second order only. For every third order minor is 0. Every fourth order minor is also 0. Therefore, rank of A is 2. Because there is a 2 by 2 minor, which is non-zero. So, we have succeeded in this plan. We have succeeded in this search. You are searching for a non-zero minor of order 2. We have got it. Previously, we could search for getting a 3 by 3 minor which is non-zero. That also we have done. But we failed there to get a non-zero minor of order 3 or 3 by 3 minor. That is why rank is not 3. Well, my dear, the two conditions which we have given in the definition are satisfied with this. Rank is 2 because there is a 2 by 2 non-zero minor. Success. Second condition. Every minor of order 2 plus 1 or more. More than 2 means 3 by 3 minors are all zeros. 4 by 4 minors are all zeros. Therefore, rank is 2. Well, my dear, you consider this example. A, and A not equal to 0. What is the rank of this matrix? Every 3 by 3 minor, 0. Because all the elements are A's. Any 2 rows are equal, any 2 columns are equal. Every 3 by 3 minor is 0. Every 2 by 2 minor is also 0. I'm very sorry, we cannot say rank of A is 3. We cannot say rank of A is 2. And then next choice is 1. Is there any 1 by 1 minor? Oh, so many, plenty. This is a 1 by 1 minor. So what is the rank of A is? 1. Rank of A is 1. Yes. Like this, we find the rank of the matrix. So, from this observation, we notice that rank of every non-zero matrix is greater than or equal to 1. Basing on this only, though some others are there who could define rank of a zero matrix is 0. Previously, we have discussed it. It is neither useful nor harmful. That is why we do not be pertinent about that. We just do not consider it at all. And for the time being, we are interested to make use of rank of a non-zero matrix only. And that is why we define a rank of a non-zero matrix only. For a non-zero matrix, rank of A is greater than or equal to 1. Minimum 1 is there because it is a non-zero matrix. At least one entry is non-zero. As it is a non-zero matrix, at least there is one non-zero entry. That itself is a 1 by 1 minor. 1 by 1 square matrix which is non-zero. Hence, rank of A is 1 in that case. Rank of A is 1. Yes. To understand the meaning of the word rank, we have taken very simple examples 1, 1, 1, 2, 2, 2, 3, 3, 3, 3, like that. And we may be getting different types of matrices with so many different elements. In that context, what is the way to get the rank immediately or in the easy way? Well, my dear, there are so many other methods. Look here. For example, we have A is equal to 1, 3, minus 1, 2, 2, minus 1, 4, 5, 3, 2, 3, 7. A matrix is there. You are supposed to find the rank of the matrix. Rank of the matrix. You see, you always observe, I am considering the examples with 3 rows and 4 columns because if you could practice well with this model, this will be very much helpful in solving linear equations in 3 variables. Yes, for that purpose only I am always considering such matrices. Good. What is the systematic procedure actually to have the rank of the matrix? Delete first column, one 3 by 3 manner will be there. Delete second column, another 3 by 3 manner. Delete third column, another like that. 4 minors of order 3 by 3 will be obtained. You go on checking every minor and you stop when you are able to get a non-zero minor. It is a risky job, you know. Suppose you go on finding 3 by 3 minors. Every 3 by 3 minor is becoming 0. Suppose it does mean that you have to find the determinant 4 times. And then again you have to try for 2 by 2 minors. It is a risky job. No. Now I like to suggest you one beautiful method. What is that method? Follow it carefully. It is available in very less number of textbooks and very few lecturers follow this method. Look here. Don't ask me how and why. You just proceed as I say. Use elementary row operations to make all the entries below the first entry, first column. After that, make all the elements which lie below the entry, second row, second column entry. And then third row, third column. That's all. Then you have the rank. I will tell you the procedure. There has been a very good procedure of obtaining this into a special form called echelon form. Don't worry, I shall explain you the form after completing this problem. You first follow the methodology, that's all, which I am going to tell you. You try to make all the entries which lie below first row, first column entry. And then make all the entries zeros which lie below second row, second column entry. Again below third row, third column entry. We are lucky we are having only 3 rows here. There are no more elements below third row, third column entry. Okay, first of all, I like to make this 0. This A is equivalent to, come on, I like to make this 0. So R2 changed as R2 minus 2R1. From this, I like to subtract 2 times of 1. What is being changed? R2 is being changed. So R1 lies as it is. 1, 3, minus 1, 2. 2 minus 2, 0. Minus 1, minus 6. 2 times of this is to be subtracted, isn't it? Minus 1, minus 6. 4 minus of minus 2. 5 minus 4. Success. We have got 0 here. One more piece of responsibility is laid on our shoulders. You are supposed to make all these entries which lie below this zeros. Okay. R3. R3 minus 3 R1. 3 minus 3. 2 minus 9. 3 minus of minus 3. 7 minus 6. Good. Luckily, we could have observed that these 2 rows are with same elements. Now you use You come to the last row, third row, you change it. R3 changed as R3 minus R2. Why should you come to the last row? In our plan, the first step is completed. We would like to make every entry below A11, that is first row, first column entry, zeros. Next, we shall concentrate on all those elements which lie below the second row, second column entry. So we'd like to make this 0. That is why I'm concentrating on third row. How can this be 0? Minus 7 minus of minus 7 is 0, isn't it? Good. R3 is changed, therefore zero, 0, 0, 0. Stop there. The so-called procedure is fulfilled, completed. Rank is 2. How? By applying these elementary operations, determinant will not change, isn't it? And we shall now produce the new sentence. Elementary operations do not alter the rank of the matrix. Yes, one of the most standard sentences. You can consider it just like Veda. Yes. Elementary operations do not alter the rank of a matrix. Well done. Observe this. Every 3 by 3 minor is 0. So rank is not 3. And there is a 2 by 2 non-zero minor, minus 1 minus 12, non-zero. Even this, minus 7, non-zero. It is enough if you can have one such non-zero minor. Happy, this is rank is 2. In this procedure, at last some matrix will be obtained. You count the number of non-zero rows. How many non-zero rows are here? Only 2 non-zero rows are here. That is why rank of this matrix is 2. And this particular form of the matrix is called echelon form. Let me describe you the nature of echelon form slightly. What is meant by echelon form of a matrix? Let A be a non-zero matrix. A is said to be in echelon form if first condition, every 0 row. What do you mean by 0 row? Row in which every entry is 0. Row with every entry as 0. Every 0 row lies below all the non-zero rows. All the non-zero rows. By the by, what is meant by non-zero row? A row with at least one non-zero entry. A row with at least one non-zero entry. That is the first one. Previously, we could have had the last position of the matrix, the last row is 0. That we call the 0 row. And this lies under every non-zero row. That is, it is placed at the last place. First condition. Next, second condition is very, very important. The number of zeros before the first non-zero entry of a non-zero row is less than such zeros in the next row. That's all. Only two. Try to understand the sentences carefully. Of course, some others like to take the third rule also. Every first non-zero entry must be 1. Actually speaking, it is not necessary, but if it is 1, it will be an additional added advantage. And it is enough for us to go through these two rules. Enough. If you can understand these two rules carefully, finding the rank is very, very easy. You can understand it. You can feel it. Yes. Let me try to explain these two rows by the means of another example. Observe this matrix. This is a 0 row. These are all non-zero rows because we are able to have at least one non-zero entry. Non-zero row, non-zero row, non-zero row. The 0 row lies below every non-zero row. First rule is satisfied. What is the first non-zero entry? 1. How many zeros are there before that? 1. Number of zeros before the first non-zero entry. How much? 1 0. First non-zero entry? 2. Number of zeros before the first non-zero entry? 2. Number of zeros before the first non-zero entry? 4. Observe the number of such zeros. Such means number of zeros before the first non-zero entry. Here it is 1, here it is 2, here it is 4. 1 is less than 2, 2 is less than 4. That is the second rule. It is in the echelon form. What is the rank of this matrix? 3. Why? This is a 3 by 3 non-zero rows are there. Enough for us it is rank is 3. Rank is 3. Suppose I change this to be some 9. Do you agree with that? This is in the echelon form. No. Can you say that rank is 4? No. You have to make this also 0. That? Okay. I think you could have observed the two rules. Well, my dear, in short tips to say in a brief way, all the entries below 1/1th place, zeros. All the entries below 2/2th place, 0. All the entries below 3/3th place, 0. That must be the rule. You keep that point in your mind. Automatically it will be converted into a echelon form and thereby you have the rank of the matrix. Well, making use of that, let us try to get the rank of 2 more matrices. What is the rank of the matrix? He is asking you. What to do? That is the basic principle. 1/1th place, 2/2th place, 3/3th place. The only thing that you have to do is you have to make all those entries below this 0, below this 0, below this there are no elements at all. So only 2 pieces of responsibility. Come on, start. This is, I like to change R2 as, come on my dear, you suggest me a row operation. This is -3. This I want to get 0, -3 plus 3. So R2 plus 3R1. 1, 3, -1, 4. -3 plus 3, 0. 4 plus 9, 2 minus 3, 7 plus 12. How much? 19. Okay. Next, third row. This is 4. This is 1. We want to make it 0. What is to be done? R3 minus 4R1. Come on, proceed. 4 minus 4. Minus 1 minus 12. Minus 3 plus 4. Minus 3 minus 16. All the entries below 1/1 place, they are made zeros. The next target is all the entries below 2/2 place. This we have to make 0. It's very simple. It's very simple. How? 1, 3, minus 1, 4, 0, 13, minus 1, 19. R3 is changed as R3 plus R2. Come on. 0 plus 0, 0. Minus 13 plus 13, 0. 1 minus 1 is 0. Minus 19 plus 19 is 0. Oh, successful. Rank of this matrix is 2. Why can you be sure of that? We are sure of it because you observe this determinant. It is 13. I am able to have a 2 by 2 minor whose value is 13. That's non-zero. That is enough for me to say that it is of rank 2. Moreover, according to our customary habit or rules of Echelon's form, number of non-zero rows is 2 at the end. Therefore, rank of this matrix is 2. Rank of this matrix is 2. Find the rank of this matrix. How to get it? First step, R2. This I want to make 0. 4 minus 4 only becomes 0. So R2 minus 4R1. 1, 3, minus 2, 1. 4 minus 4, 0. Minus 2 minus 12, minus 14. Isn't it? 3 minus of minus 8, 11. 4 minus 4, 0. R3 changes as, come on, tell me. R3 minus 5R1. 5 minus 5. 1 minus 15. 2 minus of minus 10. 7 minus 5. First duty is over. All the entries below 1/1 place, 0. Second duty, second piece of duty, what is that? All the entries below 2/2 place, this we have to make 0. Let us do. 1, 3, minus 2, 1. 0, minus 14, 11, 0. 0, 0, 1, 2. By R3 changed as R3 minus R2. My dear friends, this procedure has multiple benefits, you know. If you just consider these 3 rows, 3 columns, you have the determinant of this particular minor, 3 by 3 minor, isn't it? So what is the determinant here? Minus 14, non-zero minor, 3 by 3 minor, we are getting. Hence, the rank is 3. You observe how easy it is to have the rank. This is the finest of so many, this is one of the finest procedures which we have to find the rank of a matrix. One more. Find the rank of, observe the matrix, 1, 2, minus 1, 3, 4, minus 2, 3, 5, 5, 0, 2, 8, 1, 2, minus 1, 3, 4 by 4. The given matrix itself is 4 by 4. In order to have its rank, you may have to test for deity first. 4 by 4, there is only one minor. And it is not an easy procedure to have the determinant. It is not an easy procedure to have the determinant of a 4 by 4 matrix. It cannot be done on this part. But our procedure, that procedure which we could have learnt just now, helps us a lot. You observe the same. I am changing second row as R2 minus 4R1. third row as R3 minus 5R1, fourth row as R4 minus R1. Look here. 1, 2, minus 1, 3. 4 minus 4, 0. Minus 2 minus 8, minus 10. 3 minus of minus 4, 7. 5 minus 12, minus 7. 5 minus 5, 0. 0 minus 10, minus 10. 2 minus of minus 5, 7. 8 minus 15, minus 7. 1 minus 1, 0. 2 minus 2, 0. Minus 1 minus of minus 1, 0. 3 minus 3, 0. Again, our first duty is over. All the entries below 1 month place made 0. Next plan is to make all the entries below 2/2 place. This we want to make 0. Concentrate on that. Next one, R2 is changed as, no, R3 is changed as, R3 is changed as R3 minus R2. What is you are going to get? 1, 2, minus 1, 3, 0, minus 10, 7, minus 7, 0 minus 0, minus 10 minus of minus 10, 7 minus 7, minus 7 minus of minus 7, 0, 0, 0, 0, 0. Finished. Rank is 2. You can understand how easier it is to have the rank of a 4x4 matrix. Isn't it? That is the way we generally adapt to have the rank of a matrix. Well, my dear, now we shall be looking for the utility of rank of a matrix. Where does this concept is under use? Where does this concept where does this concept become useful? That we want to have. The very first context in which rank of a matrix can be used is solution of simultaneous linear equations. What are they? In what way do they look? What will be the nature of the solutions? What are all the different names or concepts behind them? That we see. Observe these two equations. 3x plus 4y is equal to 0 and 7x minus 8y is equal to 0. 7x minus 8y is equal to 0. Well, x equal to 0, y is equal to 0 is surely one solution. Nobody denies that. X equal to 0, y is equal to 0. 0 plus 0, 0. 0 plus 0, 0. No problem. Is there any other solution or not? Of course, there is a procedure to know, actually speaking, from this, use this equation. Let me call this 1, this 2. 7x is equal to 8y, or x by 8 is equal to y by 7 is equal to k. Say, substitute there. 3 into 8k plus 4 into 7k is equal to 0. Again, 24k plus 28k is also 0. And if you place k for anything, you have so many things. Observe the equation now. 2x plus 3y is equal to 5. 3x minus 2y is equal to 1. 2x plus 3y is equal to 5. 4x plus 6y is equal to 7. Another system. 2x plus 3y is equal to 5 and 4x plus 6y is equal to 10. Three types of systems I have put on the board. Here, x equal to 1, y is equal to 1 is a solution. There will be no more solution. Here, this will have no solution at all. You can check. Why? These two are two parallel lines, isn't it? In coordinate geometry, these two are two parallel lines. They do not meet at all. So they do not possess a common solution. Whereas that those two systems have, those two equations have infinitely many solutions. Isn't it? Well, A system of equations of this form 2x plus 3y plus 4z is equal to 0, x plus 2y minus z is equal to 0, 3x plus 5y plus 3z is equal to 0. This is one system. And x plus 2y plus 3z is equal to 6, 2x minus y plus 4z is equal to 5, x plus y minus z is equal to 1. For this system, there are no constants, arbitrary constant. For this system, there are constants. This type of system is called a homogeneous system. And this type of system is called a non-homogeneous system. What is that? Non-homogeneous system. Well, so far you might have got a big confusion about these names, isn't it? Let us have a clear-cut idea about these things.